Okay. So basically, so today is 20th of May. We have about 1.5 months left, a little bit less than that until the end of the semester. So what we covered so far since the beginning of the semester, we focused on inviscid compressible flows, yes? So basically high-speed supersonic flows and transonic flows and let's say relatively low-speed subsonic but compressible flows. So we discussed the concepts of oblique and normal shock waves, expansion waves, so all compressible flow related topics. Now this constitutes, if you remember from the beginning of the semester, this basically constitutes the first part of the semester. And if you remember again from our syllabus discussion, this aerodynamics 2 class is divided into two major sections. The first section is what we covered so far, compressible flows, high-speed flows. And the second section we're going to start discussing today with this our single 1 hour class today is viscous flows. So you may have partly, probably you were exposed to this when you were taking the heat transfer class, meaning that the effect of viscosity, let's say, in a flow that is moving around an object, a solid object. This effect of viscosity is basically, of course, this happens, the effect of viscosity is there all the time, whether you're flying low subsonic, high subsonic, transonic, supersonic, or hypersonic, it's always there. However, in some flow regimes, it's, let's say, it is less pronounced. In some flow regimes, it's more pronounced. In the context of this class, we will focus first on a viscous incompressible flow. So mostly subsonic flows up to about Mach 0.3, let's say. And the effect of, we will see the effect of viscosity. So we did, for example, if you remember when what we discussed in aerodynamics 1 last semester, we basically discussed subsonic, inviscid incompressible flows. That's what aerodynamics 1 class was all about. However, now we will extend that to viscous incompressible flows, okay? When we have the effect of compressibility, meaning if we have density changes and everything, and if the flow is viscous, it's a little bit more advanced topic. So you could see those topics if you take advanced, let's say, graduate level classes if you want to continue to your master's or PhD degrees, there are classes related to that, because that physics where both viscous effects and compressibility effects are significant, these are quite complicated flows. So we generally treat them under more advanced topics. But in this class, this is a third-year class, so we will first focus on fundamentals. Fundamentals meaning that effects of viscosity for incompressible flows first, okay? And in this regard, two main subjects are important, or concepts, I can say, are important. The first one is what we call the concept of boundary layer. You may have seen this partly in the heat transfer class as well, last semester. So, but we will go into very much detail of also the mathematical analysis, physical conceptual analysis and mathematical analysis of boundary layer flows. And also another significant effect of viscosity is that we experience on aerodynamic bodies, flying vehicles, the concept of flow, what we call flow separation and stall. So those are all viscosity related effects. So the rest of the semester is basically going to be focusing on this. So after this kind of little introduction, now let's start watching the video, but I will be here as usual. So, and I will be teaching the class in the video. This is a recording from last year, but in any case, please feel free to stop anytime and we can discuss further. And if I need to explain more during the video, I will stop myself and explain more. But in any case, feel free to stop and ask questions at any time. So let's...
Hocam.
Evet.
In our last lecture, you said we were going to kind of discuss, kind of repeat the supersonic linearized flow, but I guess you changed your minds. Am I right?
I mean, we finished the topic, but if you're interested, we can go over that as well, just to remind you.
I just wanted to say because you said it. So
yeah. Thanks for reminding me. Thanks for reminding me. Let's do this. Before we start the video, if you have any specific questions, we can discuss it. But if you want me to go over it quickly, just to remind you the topic that what we discussed, I think linearized supersonic flow was the topic.
Yes, the last topic.
Last topic, we can go over that just to remind you. But in any case, thanks for reminding me. But let's start the viscous flow topic. It's going to be conceptual anyway today. We don't have, in 1 hour, we cannot go into all the details about mathematics and everything. We will see some, let's say, concepts. And then maybe next week, if you maybe come up with some questions or if you, I mean, I cannot go over and teach you, all over again. But if there are some certain parts of linearized supersonic flow that you have not understood or you have questions in mind, we can go over it again maybe next Wednesday. Does that sound okay for you?
Okay, thank you, sir.
So let's start this, and yeah, as I told you, you can stop at any time and we can discuss. Let's see what we got here. Sorry, guys, can you hear it? I have to restart it again. Can you hear the sound?
No, we can't.
No? Okay, let me restart it again. I think I forgot to share the sound. Yeah, I had to click this. Yeah. And let's go back a few seconds back. And okay, so now, can you hear it now?
Yes.
And can you see the slide, viscous flow slide?
Yes, sir.
Yes, okay, so let's start. We are starting viscous flows. Since this beginning of aerodynamics 1, actually, aerodynamics 1 was all about inviscid flows. And aerodynamics 2, everything that we covered so far is about still inviscid. The first semester aerodynamics 1 was inviscid incompressible flows. The first part of this semester was inviscid compressible flows, and now we are starting. We are getting more real, and now we are starting to include more real flow effects, which is effects of viscosity. Yes, the real flows are always viscous, and we can when we ignore them, we can do certain calculations, as we have seen so far. Since back in September, we have seen many different things on how to analyze aerodynamic loads, how to calculate, how to use them in design for subsonic flows, for supersonic flows, for internal flows, external flows. We have seen many things, and those are very much valid. But one thing that those methods are, lacking is the lack of capability of estimation of drag. So that's what's written here. The first item, most important cost of aerodynamic operations. Yes, it's drag. So correct estimation of the drag is we can calculate some to a certain degree using whatever we learned so far until this point, but most important drag contribution comes due to different flow physics, many different aspects of flow due to the effects of viscosity. So this drag force, as it's written here, occurs due to the viscous nature of the fluid. So in reality, there is no such thing as an inviscid fluid. This is a approximation by us engineers. But in reality, every fluid is viscous. So and it does take a very important role, whether in low speed flows or high speed flows. Doesn't matter. As long as we have a fluid interacting with a solid body, this interaction causes a momentum loss on the fluid, as we will see the details later. This interaction causes, for example, if you compare the momentum of the fluid oncoming towards a solid object, when you compare that momentum level to the momentum level of the fluid after the solid object, after it's interacted with the solid object, it's not the same. It loses some of its momentum. And this momentum difference in a simple control volume analysis, basically between the inlet of the control volume, which is in front of the body, compared to the exit of the control volume, which is after the body, and if there is a difference, and there is a difference if it's viscous flow, that momentum difference is balanced by the drag force. So that drag force needs to be very calculated. It's very important for us aerospace engineers, because drag is equal to thrust, first of all, in cruise flight conditions, at least, which, like a passenger aircraft, spends most of its life under cruise condition, and under cruise condition, thrust is equal to drag. So engines have to supply just enough force, forward thrust force, to balance the drag, so the forces will be equal to each other. There will not be any acceleration, so it will be a constant speed cruise flight. So it's very, therefore, critical to estimate the drag correctly, to size up your engines, first of all. Plus, of course, the smaller the drag for those aircraft, the smaller the amount of thrust that you need, which means by this time, probably you have seen in the propulsion classes that the engines will have to consume less amount of fuel to do that. So therefore, estimating correct drag or by some means, by some theoretical means, is very critical, so that you can estimate, therefore, your fuel consumption very correctly. You don't have to oversize your fuel tanks or fill up your aircraft with unnecessary fuel, so that your aircraft will be lighter. So therefore, it's very important, and is written here, implicit assumption that we have used so far is a little too strong to capture all of this important phenomena occurring in nature and applied to aerospace engineering. And one important aspect is, we will later see, that is flow separation. So it says separated flows here, which is a very critical viscous flow phenomena, and it's very dangerous flow phenomena for aircraft. Flow separation leads to sudden drop in lift, and then you may, if you're in an aircraft, you may not, it's going to be, if you lose your lift, that's a very dangerous situation, obviously. So basically, as I was describing here, and this was experimentally proven that, and the first studies they were started by Prandtl in the early 1900s, and continued later with his students, is that when the fluid particles are moving relative to a solid surface, and when they are, as they get closer, fluid particles get closer and closer to the solid surface, they keep losing their momentum. They keep losing their momentum, and they move slower and slower and slower as they get near the surface. So if in the extreme case of when they are, let's say, at the surface, they lose their entire momentum. So they are actually at zero velocity when they are in contact with the surface. In aerodynamics, this is known as the no slip condition. Okay, no slip condition. So fluid particles that are exactly at contact with the surface have zero momentum, so zero velocity. So we know this as no slip condition. Obviously, the thing is, well, if the fluid particles just on the surface, if they are at zero velocity, if you go a little bit up above the surface near the free stream, obviously they are not at zero velocity. They are at free stream velocity. Let's call it U infinity. So if you think about the flow velocity distribution on near the solid body, then it should start from zero on the body surface, and it should go up and it should reach to U infinity somewhere above the body. The question is, how does this change occur? That's the critical question. Does it go from zero to U infinity in a, it's not, first of all, it doesn't go from zero to U infinity in a stepwise fashion. Does it go in a linear fashion, like a straight line? If we are talking about, let's say, if this is our airfoil subject to this U infinity here, so if this is zero on the surface and U infinity up here, does it go from here to here in a linear fashion or following some other function? If it's not linear, if it's following another function, what is that function? So that I need to know exactly how it goes from zero to U infinity, because that function can be integrated. That function is the velocity variation function. That function can be integrated to find out how much momentum loss I have within this region where it goes from zero to U infinity. Okay, so therefore, in reality, this region where it goes from zero to U infinity level is what we call the boundary layer around the blade. Okay, where we have the viscous effects are heavily dominant boundary layer around the blade, where the viscous effects are heavily dominant, where the fluid particles lose their momentum, and the momentum loss in turn comes back to us as drag. So the viscous flow analysis that we're going to learn in this class is very much about learning the physics of boundary layers and mathematics of boundary layers. Okay. Question?
Hocam, when the fluid particles reach the U infinity after past the boundary layer, the direction is the same as the real U infinity, or it can be deflected, or?
No, the direction will be U infinity direction. The question is along the streamwise direction. Let's say we have some kind of airfoil. Does the U infinity change as we go along the airfoil, right? For example, this is one topic that we're going to investigate. But first we will start with a very special geometry. It will come in a few slides later, which is called a flat plate. It's not an airfoil, it's just a straight flat plate. Okay, this flat plate is such that there is the pressure gradient along the plate, dp dx is zero. There will be a boundary layer around it, but the flow outside will have constant U infinity. We will first try to understand this problem in terms of its flow physics and mathematics. Then we will go, well, what if this pressure gradient was not zero? Or what if we have some varying U infinity? How should we modify our equations? We will see those later. But in the simplest sense, to understand the concept, we assume U infinity the flow reaches to the U infinity level, meaning that it reaches that its magnitude and its direction of the fluid particles. Fluid particles have the velocity such that its magnitude and velocity direction is the same as U infinity. Okay.
Thanks.
So yes, let's continue. So this is just a typical description of flow around an airfoil in real life. So in real life, meaning now including viscous effects. So we have all these nice streamlines oncoming towards the flow. Just a second. Okay, we have this. I have to go to show mode, I guess. But anyway, we have these streamlines coming towards the airfoil, and then the airfoil is sitting at a certain angle of attack with respect to the flow direction. And here, as soon as the fluid particles start touching the airfoil surface, I mean, there, first of all, let's say there will be a stagnation streamline. This stagnation streamline will hit the body, and we will have a stagnation point where all momentum is zero. Then the flow will start to develop on the body surface, such that the fluid particles near the body surface will have reduced momentum, and if they are on the surface, they will have zero momentum, no slip condition. And as this develops, the velocity profile will take a shape as shown here. I will try to mark it, but it doesn't. Okay, as shown here, right? So there will be a zero velocity here, and it will asymptotically reach U infinity along a normal to the surface. So this will continue over the suction, the top surface and the bottom surface, or the suction and pressure sides of the airfoil. And we will have what we call the boundary layer on the airfoil. Now, in real life, there will be a pressure gradient along these surfaces, and we have learned how to calculate those, right? We have learned, for example, how to calculate CP distribution on an airfoil, which is the pressure distribution on the airfoil. So depending on the airfoil shape, by this time you know that this pressure distribution can increase, pressure can increase along the way. So as you are going on the surface of the airfoil, can increase or in some regions or decrease in some regions, right? Generally, in a typical airfoil geometry, initially after the stagnation point, the pressure strongly drops, it gets reduced, and it reaches to a minimum pressure level. That's called the maximum suction point, because suction is generally negative pressure. Negative pressure means negative local static pressure on the surface will be less than the static pressure at P infinity. This is right, in fact, how we define CP. If you remember, P must be infinity over 1/2 rho U infinity square. So if local static pressure is below P infinity, CP will be negative, and the thing will be, the physical situation will be, there will be strong suction. Then the pressure will drop until some point, and then it will start, once it reaches the maximum suction location somewhere on the airfoil towards the leading edge, then pressure will start to increase again. This is, if you remember, let me draw here, typical CP distribution, right? CP, and you know that we have reversed axis. Let's say this is X over C, and we have CP will go to a suction peak. Okay, so CP axis is reversed. This is minus, and this is plus on this side. So you reach a minimum CP, and then it will start to increase. Pressure will start to increase. Now, depending on the angle of attack of the flow, this pressure increase can happen very sharply or very smooth in a very shallow fashion. Now let's say somewhere here we have the suction peak, and then after this, as you move along the surface, now pressure is increasing. Just two definitions for you. If when you're moving along the surface and when you're moving along, if the pressure is dropping, so the fluid particles are moving in a region where as they move, the pressure is reducing, this is called favorable pressure gradient. Favorable pressure gradient. If they are moving towards an increasing pressure, this is known as adverse pressure gradient. Okay, so when they are in the adverse pressure gradient in the CP plot, this is that region. This is the adverse pressure gradient region. The region before the suction peak is the favorable pressure gradient region. So this is favorable, this is adverse, and suction peak is here. Now, when you are in the adverse pressure gradient region, is that fluid particles are moving towards an increasing pressure. I mean, normally that's as you know, this is not something normal, right? Normally, fluid motion happens from high pressure to low pressure. The natural motion of any fluid happens from high pressure to low pressure. But here, the fluid particles are spending their already existing kinetic energy and momentum to move against an increasing pressure in an adverse pressure environment. Well, if depending on the level of their kinetic energy, this can happen up to a certain point. They can move and move and move, but every time they move, since they are moving against an increasing pressure, they keep losing more and more momentum. And if the angle of attack is high enough, therefore the adverse pressure gradient is, let's say, adverse enough, which means that the pressure is high enough, at some point they will not only lose their momentum, entire momentum near the surface, just on the surface, just very near the surface, they will have extremely low momentum and kinetic energy, such that they cannot have any kinetic energy to move forward anymore. At that instant, the flow and therefore the streamlines, what we call, separates from the surface. Streamlines are not able to, or the fluid particles are not able to follow the surface geometry anymore. Normally we expect that they would, but now they cannot do that anymore because their momentum and kinetic energy is not enough. They separate and they follow a different direction. And this is called separation. And this separated region is full of vortices. And, on the airfoil surface where we have separated region, the pressure distribution becomes almost flat, so it entirely changes the load on the aircraft, and the lift suddenly drops very quickly. All the physical phenomena that I described until this point is because of the fact that the generation of the boundary layer, the separated flow process, and therefore the consequence of having lift reduction is all related to the viscous flow physics. So some of it is described here in detail. So on the top plot, we see static pressure distribution on the surface. Which surface? The surface that is given here. When you follow the when you walk along the surface from, let's say, S1 to S1 to S2 to S3, so you see this on the x-axis on the plot, you see that in the region of adverse pressure gradient, we have continuously increasing pressure. So P3 is larger than P2, P2 is larger than P1. So yes, the fluid particles are trying to move from left to right with their existing momentum and kinetic energy, but they are moving in an adverse pressure gradient environment, which is kind of opposing the flow, trying to stop the flow, if you want. So in that case, if this is our velocity variation here, if this is our velocity field variation within the concept of the boundary layer, here's our fluid. This gets pushed back. This is to move against the big resistance, and then at the separation location, let's say this is at 2, the velocity profile becomes different, and I mean the concept of the whole boundary layer aerodynamics is, first of all, to find the shape of this curve within the boundary layer, velocity profile curve, and then what happens, how that curve changes, how that shape changes when we have separation. You can see the curve has an inflection point now, and then after the separation we have a totally different curve. How do these changes happen? Can we actually develop enough mathematical tools or background to represent these effects at least up to a certain degree? So for analytical calculation of these flow characteristics, if we can, some numerical calculation of these flow characteristics as well. So in order to find all of this, so the thing is, it's a question of not only it's a question of finding the drag correctly, or at least estimating it more or less correctly. It's also the question of finding the separation, dealing with the separation. Okay. By the way, we are doing these in class hours, but most probably I will go until 2:15. I will give a short break because its online courses are a little. We are covering more material, so at 2:50 I will give a short break. I will have another probably half an hour session, another break, and we will conclude at 3:30. Okay, so we now come, yes, to the concept of the boundary layer, which we started discussing. So the concept of boundary layer, it's as written in this definition here, it's the region of a flow in the immediate vicinity of a wall where fluid motion is dominated by viscous forces. As I tried to describe before, and the sketch here is given for a very simplistic geometry, the one that I called as flat plate before. So let's write this down. This simplest. Our first analysis will be based on that. So this is flat plate. So before the flow reaches the solid body, in this case the flat plate, let's say we have a uniform with a certain amount of momentum level, certain amount of kinetic energy that can be calculated. But now, as soon as the fluid particles get in contact with the solid body, right, starting from the fluid particles that are in touch solid body, which will have zero momentum, no slip condition, and at the free stream they will reach, let's some kind of u infinity level. Let's say this is u infinity here. There will be a distribution within this region. So this region is called boundary layer, as marked by this bluish region here in this sketch. The thing is, as the fluid particles move downstream, more and more momentum loss will start building up. Okay, because initially they will, the amount of fluid particles that are in contact with the body is not much. They will keep losing and losing and losing the momentum as they go in the streamwise direction. So therefore, connected with this, the extent of the boundary layer, so that, or what we call the thickness of the boundary layer, will get higher and higher and higher, and it will of course reach to an asymptotic value, but it will basically grow as we move along the body. The boundary layer height, or what we call boundary layer thickness, keeps growing as the fluid moves in the streamwise direction along the body. Okay. Of course, in this sketch, we are only showing the top part. If this flat plate is exposed in, fully in a flow, there will be a boundary layer also in the bottom part. So this boundary layer grows and grows and grows. Generally, we describe this boundary layer height with the Greek letter delta. Okay, as written here. I will come to this in a second. So this delta is growing. So as we move along the flat plate, if I move, if I put a coordinate system, let's say this direction is x, and this direction is y. I will try to draw a line. Yeah, normal to the surface of the flat plate. So delta will grow with x. So delta is a function of x. The question is, we don't know what this function is, how it grows. And we want to calculate it under different flow conditions for different geometries, for flat plate, for airfoils. How can I calculate this delta? Okay, because the thickness of delta definitely determines it directly determines the extent of the region where I have lost momentum. Okay, and that momentum loss, I know that it is related to the drag force, as I described earlier. So therefore, I want to calculate how this delta changes. So as we come here, velocity at the outer edge of the boundary layer. So just at the top boundary of the boundary layer, I can say we call this UE. Okay, edge velocity. And this is determined by the freeze. Generally, the definition of delta, the boundary layer thickness, is that delta is the distance, along y coordinate, so amount of y. Delta is the distance where u, the velocity, becomes equal to, as written here, let's say, let me write it this way, 0.99 of UH. Okay. Now, for a flat plate problem, this edge velocity is equal to basically U infinity. But for an airfoil problem where U infinity may be changing, UH will be also a function of X, but we will come to that later. For this problem, first of all, let's write in parentheses, U is a function of UY, right? And we don't know what that function is. We want to calculate. That's the variation of U along Y. But at a certain Y location, U will reach 0.99 of UH. At the location at which this happens, we call that the boundary layer thickness. At that X location is equal to this, and we call that the delta value at that location is equal to that. So this is how we define the in aerodynamics the boundary thickness, delta value. Now, okay, there are few other length scales. Delta is the most fundamental one, the boundary layer thickness. There are a few other lengths that are of importance in aerodynamic analysis of viscous flows. And let's give a short break, maybe 5 minutes. So it's 2:15 now. Let's start at 2:20. Okay, let's give 5 minutes break. Then we will continue with the rest of the slides and with the other length scale definitions. So I will Okay, so of course those comments for the class times last year, but until this point, we have in this video we have learned this conceptual definition of a boundary layer and the first important parameter of a boundary layer, which we call the boundary layer thickness, the delta value. As I've explained in this video, delta changes with x. So along the flat plate, for example, it changes with x. We would like to calculate how it changes. That's one of our objectives. And we will see that delta change along x is actually a function of the velocity profile inside the boundary layer. The velocity profile meaning the u variation, velocity variation along y direction at each x location. And that function is not easy to obtain, but we will see how these delta is related to the velocity profile inside the boundary layer. I mean, I say velocity profile because, I mean, outside the boundary layer, for example, for a flat plate, it's equal to, we have a velocity u that is equal to u infinity. Deep inside the boundary layer, exactly on the surface, the velocity is zero. So it changes from zero to u infinity within the boundary layer. The question is, how does that change happen? I mean, does it follow a linear function? Does it follow some kind of second order polynomial? Is it an exponential function? That is very critical to know. And we will discuss all these issues. Why is it critical? Because we need that information so that we can calculate the value of delta at each streamwise location. And as finally, like I explained in the video, why would we be interested in calculation of delta? Because delta tells us I mean, by proper integration, we will see that later, we can calculate how much momentum loss happened in the fluid, in the airflow. And that momentum loss comes back to you as drag force acting on this solid object. Because if you do, even we do it in simple in our fluid mechanics classes, if you do a simple control volume analysis around this flat plate, let's say you compare the incoming momentum with the outgoing momentum, you will see that the outgoing momentum is not equal to incoming momentum because of this boundary layer effect. So there is a momentum loss, and from simple control volume analysis, you can relate it to the actual viscous drag force. So that's why the calculation of drag is, as much as accurate calculation of drag is required, so that in order to do an accurate calculation of drag, we need to know basically the boundary layer properties, the delta variation, the velocity profiles, and also in addition to delta, we have other length scales. We will see those later, and like displacement thickness you are seeing on the slide right now, and momentum thickness. Those needs to be accurately estimated by theory. At least up to a certain level. If you cannot estimate by theory, we need to do experimentation in wind tunnels, okay? Because it's very, very difficult to do this, or probably impossible to do this during a flight test of a vehicle. So we do, if we do not have good enough theory, we need to do at least wind tunnel tests to come up with these viscous flow related parameters, okay? Anyway, so let's, if you have any questions, I can try to answer. Otherwise, let's stop at this point and continue next week. And also, as I said in the beginning of the class, please revise the video before this, the previous video on linear supersonic flows. As I said, I cannot go over the entire class one more time, but if you come up with some questions, if there are sections that you do not understand about this, I can revise that as well in the next, before we continue discussing the viscous flow part next week, okay? Do you have any questions? Yes, I'm listening.
Can I ask something?
Of course.
We can see the acceleration of the flow on the upper side of the airfoil, cambered airfoil or symmetric airfoil, if have the angle of attack.
Yes.
So the flow turns to be subsonic to supersonic.
If, let's say, you are above M critical, yes?
Yes. The boundary layer phenomena, how develops the boundary layer? It's change?
I mean, the flow could be subsonic or supersonic, but in all cases, in reality, I mean, in this class, we are right now focusing on, low subsonic incompressible flow, but in reality, let's say you are flying at a Mach number that is above Mach critical, yes? There will, and there is, let's say, a supersonic pocket over the airfoil, yeah? There will still be a boundary layer, okay? There will still be a boundary layer. The Mach number will be locally, let's say, supersonic in some regions, and it will be locally subsonic in some regions. And there could be probably a normal shock wave somewhere downstream of the supersonic pocket. And then, so all those physics will be there. On top of that, there will be a boundary layer. There will be an existing boundary layer, and the thing that we talk about, for example, we define this thing called edge velocity, right? Edge velocity. The edge velocity is it corresponds to these Mach number changes we discuss in the sense of inviscid flows. Okay, so if it's locally supersonic, and if you are telling me, like, say, okay, look, professor, in this top, in this part of the airfoil at the top, at, I don't know, 40% of the chord, suddenly there's a supersonic flow and Mach number is 1.2. So in real life, there will be a boundary layer, and which then I translate that information into this. Okay, if Mach number is 0.2, I'm sorry, 1.2 at that point, which actually means my edge velocity, and therefore actually edge Mach number is 1.2. And there will be a boundary layer. How thick is that boundary layer? I don't know. It needs to be calculated. Okay, so that's how I can explain it.
Thank you.
Any other questions? Sorry. Okay, then. So let's pick up from this point next week, and we will discuss more. As I said, if you come up with some questions regarding this linear supersonic flow, please do so, and we will discuss that as well. Great. So I will see you all. Not many people are here, but I will see you all next week.